Having talked about the magnetic force of by a magnetic field on charged particle moving in a magnetic field, then we would expect that if we have a conductor, for example, carrying a current, and that conductor is placed in a magnetic field, then that the charges which form the current should feel a force. So each one of these should feel a force. So the whole conductor actually will feel a magnetic force when placed in a magnetic field. And this is indeed the case. So, and to illustrate this, if you do an experiment, so assume that we create a uniform magnetic field here in this area between the north and south poles of a permanent magnet, and we this is usually a uniform field, and we have a wire, straight wire, and make it pass through this area. Schematically, we can show it this way. We can say that this portion of the wire actually feels or is in a magnetic field, is immersed in a magnetic field, uniform magnetic field, which is into the page. Now, when you don't have a wire, a current flowing this wire, then nothing happens. The wire remains straight. Now, if you let a current pass through this wire upwards, then you will see that the current will, the wire will be bent to the left, which is an indication that there is a force acting on this wire, pulling it to the left. Well, in contrast, if you switch the direction of the current so it's downwards, then you will see that this wire is bent to the right, okay, telling us that the direction of the force has been reversed. Okay, so as I said, we expect that the force on this current carrying wire is actually can be thought of as the sum of the forces acting on all the charges that are moving and within that wire and forming the current. So let's try to derive an expression for the force on a straight first of all, a straight current carrying wire in a magnetic field, in a uniform magnetic field, along this line of thought. To this end, we consider a wire which has a length L, and it carries a current I. The cross-section area is A here, and this is immersed in a magnetic field which is into the page. Now, the charge carriers, we take them as positive charges, and they have a drift velocity Vd, which is the same as which are in the same direction as the direction of the current flow naturally. Okay. Now, when you when the current flows in this wire, and this wire is immersed in a magnetic field, then in this case, each charge carrier of charge Q will feel a force which is Q Vd cross B. Vd here is the drift speed of the charge carriers in the wire, which we have encountered before. Now, the total volume of the wire of length L is the cross-sectional area times L, so it is this. Now, the number of charges in this segment, in this volume, is just N multiplied by AL. N is the density of charge carriers, how many charge carriers you have per unit volume. So when you multiply this number with the volume, you get the how many charge carriers you have within the whole volume of this wire of length L. Now, the current, we know the expression, of course, of the current. This is the expression for the current in terms of the as a motion, expressed as a motion of the charge carriers. And therefore, what we say is, well, each of these charge carriers, which has charge Q and drift velocity V, will feel a magnetic force just the way that we know it, and it's be given by QVD times cross B. Now, because all the charges are the same, and they are all, we assume that all have the same drift velocity, magnitude and direction, they have the same speed and they are all pointed in the same direction, then we expect that the total force on all the charges of the current will be just what? Will be just the total number of charges in the wire, which is this number, multiplied by the force on each single charge carrier, Q. Because we will have this, we will have NaL copies of the same force. They are all in the same direction. They all have the same magnitude because all the charges have the same Q and have the same Vd. And so just multiply the force on a single charge carrier by the total number of charge carriers in the wire. Now, keeping in mind, taking this in and noting that this is the current, then we can write this in this form. So QNA, in this case Vd, will be the current I, and multiplied by L. Now here we define a new vector now, which is L, which has the same direction as the drift velocity, or as the flow of the current actually, and its length, the magnitude of this vector, is just the length of the wire, because I'm talking about a straight wire. Okay, so this is how I get this expression. Okay, so I define just a new vector. I here is just this quantity here, okay, with the magnitude of the drift velocity now, Vd I, because I is a scalar quantity. So you just when you substitute the magnitude of the drift velocity. The vector nature is attributed now to a new vector that I define, which I call it L, which is the length vector of the current, and this vector has direction as the direction of the current flow. So this is the expression for the force exerted by a magnetic field B on a straight wire carrying current I. Okay, and in this example, if you look, for example, at the force, direction of the force acting on each charge carrier, according to the right-hand rule, B is inside, V is in this direction, B is into the page. So my right-hand side, I'm going V, and you close towards B, and the force will be up. The same applies actually if you apply this relation, you apply the right-hand rule to this relation. Now L is in this direction, B is into the page, so again, L cross B will be upwards also, as we expect, because at the end this force is just the sum of the forces of these FB forces acting on each charge carrier, and they are all pointing in the same direction. So this is the expression for the magnetic field, the magnetic force by a magnetic field B on a straight wire of length L carrying a current I. Now what if the current carrying wire is bent, is not straight in this case? Okay, so like for example we have this expression. Of course the magnetic field in general doesn't need to be uniform. Here it's shown it's uniform, but it doesn't need to be uniform actually. The magnetic field also can be a variable magnetic field, so it can vary over the length of the wire here. So what to do in this case? How we can find the magnetic force on this wire, irregularly shaped wire? Well, we are now experts and we know what to do. We say, okay, we have to divide this wire into small segments, each of them is ds, and we define ds vector to be in the same direction as the flow of the current at that portion. So at this port here, the ds is here. If you take a ds here, it is vector that's pointing in this direction upwards. Here it is vector pointing in this direction, and so on. And what you do, you say, okay, df, because now this is infinitesimally small, so it's straight. Okay, so you can treat it as a straight wire, a straight wire carrying a current. Okay, so we can apply the relation that we have just derived. So the force element on this ds, on any ds, is given by ids cross b. And therefore, what is the force therefore on the whole wire? Well, we have to add these up together. We vectorially add the forces on all these ds's that cover the whole wire. Now these ds's are vectors, however. So actually we integrate. Adding up these now means integration. So we create this integral. Now here the assumption is that the current in the wire is uniform, so you can take it outside the integral, and this is integral from A to B. A to B are, you know, the two ends of the wire in this case. So this is the formal expression for the force on an irregularly shaped wire in a magnetic field, and this magnetic field, as I mentioned, doesn't need to be uniform. This is a formal expression, and of course, gives you that force, and this is a reflection of the vector sum of the forces on each on the DS's that form the whole wire in this case. So try to do this checkpoint before we proceed on. And let's proceed now by considering an example where we will apply what we have just learned to this particular example. What is our example? Well, our example, we have a wire, and this is in the form of a semicircle, and the current is flowing in it counterclockwise. This lower part here is straight, and of course it has length 2r, it's a diameter, and this is a semicircle which has a radius r. Okay, it's placed in a uniform magnetic field, and the magnetic field is along the y direction. I'm assuming that the current here in the lower part is flowing in the x direction, where here it's flowing in this direction. I want to find what is the force, the magnetic force on this whole current, on this whole current carrying wire. Okay. Well, of course, we have two parts. We have this part and this part. So I can find the force on this part, and then I find the force on this part, because these are a bit different. Evidently, one can, this part here is a straight wire, so I can apply the formula that I have just learned. I mean, I multiplied I L cross B. L in this case is a vector which has length 2r, because it's a diameter, okay, and it's directed along the direction of the current towards the positive x-axis, and B in this case is the magnetic field. So I can apply this, but just for change, we will apply the general formula of integration to this side only, as well as to this part only, to this part also, and then we will find the net force on the wire. So let's look at this part. Now, the general formula is that the force F1 is the force on part 1. It is integral from A to B. A to B means A is here, B is here, because it's the two ends of the wire. Integral of ds cross B, ds cross B. So we divide this into small ds's, and we take the cross with B. Note that in this particular example, B is uniform. Okay. Now, the ds's obviously in this case are what? Are along the, all of them are along the positive x direction. Okay. And they are all along the x direction. So all of the forces on each of these ds's is the same actually, because they are all in the same direction. The magnetic field is in the same in the y direction. So the force is the same. What is the direction of the force? Well, ds is in this direction, and the magnetic field is in the, you put your hand, right hand fingers towards the direction of ds in this case, okay, and cross B, you close towards B. B is in the y direction, so this way. So it is out of the page. Out of the page in this geometry means along the positive z direction, which means along k. So the force is along k actually. Okay, so ds cross B is a vector along k. What is the magnitude of this vector? ds multiplied by B multiplied by sine theta. But theta for all the ds's is the same. It's just pi over 2, because, you know, the magnetic field is perpendicular along the y direction, and so it's perpendicular to the x-axis, and the ds's are along the x-axis. So actually this reduces to b dx. The length of ds in this case is dx. Therefore, this reduces to b dx k. And k here is just a constant vector. So you need to integrate this. Now a and b goes, because this is the origin, this goes x from minus r to x to 2r, to plus r. Okay? So this is the integral. Now b is constant, k is constant. So we take this outside. What remains is integration over dx from minus r to r, and this is just 2r. So this is the expression you get, 2ir b along the k, out of the page. Okay? Well, will this be, so the magnitude is 2irb. Is this what we will get if you had applied the formula I L cross B? I mean this formula? The answer is yes. So why is this so? Let's look here. Now I, L cross B. So the magnitude, the L is this, B is this. The angle between them is pi over 2. So it's I, L, B sine pi over 2, just I, L, B. L is the length of the wire. What's the length of the wire in this case? 2R. So I will get I, L, 2RB, which is this. And the direction is L is in this direction, B is in this direction, L cross B, so it's out of the page, or L towards B, so it's out of the page along the K. So indeed, had you applied the formula of the magnetic force on a straight wire, current carrying wire in a magnetic field, immediately to this part, you would get the same expression. Here we have just demonstrated that if even using the integrals, you get integral use this, and it's a good exercise to carry out integration, although you don't need that. Okay, it's redundant. Now we come to the circular part, which is a bit more complicated. So again, we divide this into DS's, and one DS is shown here in this case, and we find what is dF2, which is the force on this DS, for example. Okay, this DS here is an arc which subtends an angle d theta, and it is at position theta with respect to the x-axis. So the IDS cross R in this case will be, if you look at it, what's the magnitude of this? First of all, let's look at the direction. If you look at the direction, DS now is in this direction, and the magnetic field is towards the Y. So you put your right hand fingers here and close towards the direction of the field, which is along the Y. Okay, so this is your DS, for example, shown in the figure. This is the magnetic field here. So close towards the magnetic field. Your thumb is into the page, so it is along minus K. Okay, so this explains this minus sign. So it's minus K. What about the magnitude? Well, now DS and B are not at right angles, but an angle theta actually. Now, geometrically, you can, with some trigonometry actually, you can show that this angle and this angle are the same. So the ds cross b as a magnitude is modulus ds modulus b sine the angle between them. The angle between b and ds is this, which is the same as this angle, as I said. Okay, so you will have minus I b ds sine theta, ds sine theta. But what is ds? ds is just the radius multiplied by d theta, which is the angle subtended by ds. So this is ds, and therefore in this case f2, instead of ds you write r d theta. And so when you want to find the total force, you add up all the df2s. So this means integrating over the whole current. Now immediately once you see ds is equal r d theta, the integration variable is theta in this case, and so this is your integral. And the integral here, when you want to sum over all the ds's, actually means theta varies from 0 here up to pi here, and so these are the limits of integrals. You integrate, and as you can see, so this boils down, because r is constant, I is constant, and b is a uniform magnetic field, so it boils down to carrying out the sine integral, which is a simple and straightforward integral, and then eventually you get this result. Okay, so this is the force by the magnetic field on this curved part of the wire. Note that it is exactly equal and opposite to this force. So therefore the net force, if you ask what is the net force on this loop now of wire, because it's a closed loop, actually it is 0. But note that the forces are acting in different points, because this force is acting here, this is acting on another point. So as we will see shortly, this leads to a torque actually. So while this doesn't experience a net force, it experiences a net torque when it's placed in the magnetic field. But this is the how you can calculate this force. Now, when we have a uniform magnetic field, when we have a curved wire or an arbitrary shaped wire in a uniform magnetic field, if the magnetic field is uniform, then we have a special case and two special cases, important special cases. The first special case is the following, given by, it says this: consider this is, to illustrate, consider this wire here. This is an arbitrary shaped wire which has two ends, A and B. The vector L here is a vector which goes from A to B, okay? So it's like, you can think of it as a displacement. If you move from here to this point to this point, this is the displacement vector, okay? So this is the whole, you might have traveled the whole distance, but your displacement is the vector that goes from A to B, the end points, okay? So this is the vector that joins these 2 points. Now the result is, if you want to integrate, you find this integral, because how you calculate the force on the curved part of the wire is just using this integral, okay? But when B is uniform, you can take it outside the integral, and this reduces to, so the integral reduces to integral from A to B of ds. When you add up all these ds's, these are vectors, and when you add them vectorially, actually they lead to what? They lead to this total displacement. You can convince yourself. Think of these ds's. One ds here, the other here, the other. You are adding them vectorially, okay? So when you add them vectorially, they will end up actually with this vector. So when the field is uniform, even if the field is not straight, okay, but the force on it is equal to the force on a straight wire connecting the endpoints and directed along the direction of the current, okay? So it has, this L goes from A to B because the current flows from A to B. And in this case, you can use this formula immediately without the need to carry out integration. We can prove this actually here. Look at this part. The current is flowing from here to here. So this is A, this is B. And therefore, the vector in this case, L, goes from here to here, okay? So this is L in this direction. So it will go from this point to this point. It's directed in this direction, okay? Now, so you have a, so if you apply IL cross B to this, this is L and, sorry, this is L here and B here. So if you close, this is your right hand fingers towards L and you close towards B. It will give you what? A vector into the page. So it's minus K. And what's the magnitude? IL cross B, the angle between this L and the B is pi over 2, so it's ILB. And L is 2R, so it's I2RB, but it's along minus K, so it's minus 2IRBK, which is exactly the result that we have got from integration. Okay? So we have tested that this result, which is a very interesting result, an important result, but the condition for applying this result, don't forget, is that your field should be uniform. Okay? Now, the other interesting result also applies when we have, again, a uniform field, but in this time, if the loop is closed, okay? I mean, if the current carrying wire forms a closed loop. In this case, this integral reduces to, you can take B outside, and this becomes you put a circle here telling you that this is an integral over a closed loop. So you are adding up all the ds's over the closed loop. Now when we added up the ds's here from A to B, they formed this. But if this closes and comes back, then summing all these ds's vectorially will lead to 0. The meaning of this is that this integral in this case for a closed loop is 0. Any integral, by the way, of these over a closed loop is 0. Now when B is uniform, you can take B outside, so it will be B crossed into a 0, and which is 0. So our result is, whenever you have a closed loop of any shape, completely arbitrary, but it's closed and carrying a current and is in a uniform magnetic field, then the net force on that loop is equal to 0, but not necessarily the net torque. And this is exactly what we have found here. This was the closed loop, and we have found that. We have calculated the force on it. We have calculated the force on the lower part, which was this. We have calculated the force on the upper part. So when you find the net force, it is just 0. Okay? So this is verification of this result. Now, before closing this subject, there is also something, an interesting phenomena that we should also discuss and understand. And this phenomena is when you have two wires, for example, straight wires, okay, and both of them are carrying current. Now, each of these wires, as we have learned in the previous videos, when we talked about the source of the magnetic field, and if this is a straight long wire, then each of these generate its magnetic field. So this wire generates its magnetic field, and so this wire is in the magnetic field of this. And so it will feel a force when they are next to each other, because it will fall in the magnetic field of this wire, and so this will be a wire in a magnetic field and it will feel a force. The same applies to this. This will feel a force, a magnetic field coming from this second wire, and so this will be, if you look at this alone, it will be a wire feeling of a magnetic field. And so it's, since a straight wire carrying current and it's a magnetic field, it will feel a force. Now, what we will do now is we will derive the expression for this force. So let's start with the following. We assume for the time being that we want to find the force on the wire, which we call it, label it 1, which carries current I1, due to its presence in the magnetic field of wire 2, which carries current I2. So I have I1, I have wire 1 in the field generated by wire 2. Okay? So I call the magnetic field generated by 2 B2. They are both wires have the same length. So this wire will be in a magnetic field. Okay, I call it B2. And since it has a given L, and L is a vector in this direction, it will feel a force. Now, this B2 is the magnetic field due to this wire, which is wire 2. What is the direction of this B at the position of this wire? Well, look, these are in the plane of the page, okay? We know that for a straight wire, the magnetic field lines are circles, concentric circles that are centered at the axis of the wire. And they have the magnetic field lines on these circles is given by the right-hand rule. So in my case, I2 is flowing in this direction. So the magnetic field circles are circles which have arrows on them, which is rotating in this direction. So coming out of the page, okay, in this direction. Now, when one of these circles hit this, it is the magnetic field there will be tangent to that circle. When you draw a tangent, it will be out of the page. So the magnetic field, direction of the magnetic field generated by wire 2 at all points on wire 1 is out of the page because of what we know about the magnetic field lines of a long straight wire that we have discussed earlier. And so this wire 1 is in a magnetic field that is coming out of the page. Its current is flowing in this direction to the right. Okay? So if you apply the right-hand rule, L close towards B. L is in this direction. B is out of the page here. It's hard. So L cross towards B, your thumb is downwards, and this is the direction of the force. Now, since this is normal, this is tangent to the circuit is tangent here, and this is normal, so the angle between B2 and L in this case is pi over 2. So as a magnitude, B2 is mu naught I2 over 2 pi A. Where did I get this from? This is the magnitude of B2 first. This is from our previous discussions, where we found that the magnetic field of a long wire at a distance A from the wire is just given by this expression. Now, so this is B2. So the force, as I mentioned, the magnitude of F1, which is the force by this wire 2 on 1, is I1 L B2. Why? Because sine theta in this case is sine pi over 2 and it's equal to 1. So it's I1, the current that is feeling the magnetic field. B2 is the magnetic field coming from this wire, which is this. L is the length, is this length. Now, you can connect them together and it will be in this form. So this is the force, the magnitude of the force that wire 2 exerts on wire 1. And this is downwards. These are parallel. Now you can repeat the same argument for by assuming that the field, that 1 generates a field at the position of 2, wire 2, and then calculate that the force by this field on the force exerted by this field on wire 2. Now, if you repeat that argument, you will see that the force in this case will be upwards. Let's do it first, the direction, and then we will tell you that the force should have the same magnitude also. Look, because the current, the magnetic field generated by I2, to find the magnetic field generated by I1, by wire 1 at the position of wire 2, the magnetic field lines of wire 1 are concentric circles centered along the wire. But they are now rotating in this direction because the current is flowing in this direction, so the circles are flowing in this direction. So when we have a circle coming, flowing this direction and coming and hitting here, the tangent to that circle at all points on 2 are into the page. Okay, they are into the page. So these are into the page, and L now, the vector L here, is along in this direction, and B is into the page, into the page. So when you close the force now on I2 due on current 2 or wire 2 due to the magnetic field of wire 1 is upwards. Now you can check that the magnitude is exactly equal to this. So actually F2 will be exactly having this magnitude, but it's in the opposite direction. But this is only normal because these are action-reaction pair. If this is attracting, if this wire is attracting this, then this wire will be attracting it with a force equal magnitude in opposite direction. You can also check, and please do this at least for the direction, that if the wires, if the currents are in opposite directions, then these two, the forces will have the same magnitude eventually, but the forces will be repulsive forces. So this will be, 2 will be, the force by 2, by the field of 2 on 1 will be upwards. The force by the magnetic field of 1 on 2 will be downwards. So they will be repelling each other. And therefore, we get the following result. If we have 2 parallel long wires carrying currents I1 and I2, then they exchange a force. That's one of them due to having each one of them in the magnetic field generated by the other. And the magnitude of this force is this. Okay? I'm assuming here that they have the same length. Okay? If you divide by L, by the way, you get the force per unit length in this case. So F1 over L and so on, you will get the force per unit length. This magnitude of the force is the same. So it's each one, this is the force exchange, the force that each one exerts on the other. If they are their currents flow in the same direction, the forces are attractive, so they attract each other. If the currents flow in opposite directions, the forces are repulsive, they repel each other. Okay, and these forces are measurable, and you can measure them actually, and in the lab also. Okay, so this is an application where we combine what we have learned earlier about the sources of the magnetic field and about what we have learned in this video about the force on a straight wire that carries a current when you put it in a magnetic field.